Okay. Good evening, everyone. Um, Thanks for tuning in if you're tuning in, and we're going to get started. I do have a headache again today. I think it's just one of those things right now. So it will be a shorter session, but I'm going to go back to session one and I'm going to practice my NumPy and working with the vector math portion of this and going between writing that out and maybe trying to write out some of the other preliminaries, like examples from the other books. I think that and actually doing that part again would be a good and useful thing for me to do. So we're going to be doing that, and I'm just a bit low energy today. So I pulled that up and okay. So I just have this notebook that we did originally, and I'm going to start there. I want to pull up NumPy as well. Hmm, trying to get them to broadcast the same shape. I think. So if that doesn't work, I can't just add a row. And if I did, okay. Okay, let's try. Incomplete input. Oh. I think I have to relearn types for this type of thing. Like, I'm not used to working with NumPy. I typically don't have to because I work as more at the statistical end of data science, the predictive end, modeling. So now I have to figure out how to deal with types, which is why I can't add. So I'm going to get on Stack Overflow and I'm going to see if I can figure out how to do this. Oh, let me. Index here. Huh. So I'm going to need to understand how to, like, I guess the data structures of vectors in like a coding space and how to do it. Because I don't remember the math of, I know you can't add vectors of different sizes, but if they are different sizes, how do we fix that? So I transformed the first one, but there are two different links, right? So broadcasting didn't work for me. And so I thought it would. So I wonder if so I guess broadcasting doesn't work if one of these is one. Like if I were to get rid of these two and make that a plus, would that work? Um, yeah. So broadcasting only works if one is a single vector to a matrix, but not if I needed to like add a row of zeros, which I guess wouldn't be the right mathematical thing to do. Okay. So let's see if we can't find any practice problems that might help. So here, I found this Medium post. And it's talking about determinants. Oh. And I understand what a vector is. Oh, goodness, what a Friday. Only 8 more days, right? No, about 10 more days of this. It's the hardest thing to show up and make yourself study something. That is for sure. Any ounce of learning I'm getting from this is hopefully going to make a difference. But part of me wonders if I should just focus on becoming a better statistical data scientist. But I also know that like AI algorithm development depends on this. So if the market heads this way and I'm behind on just the fundamentals, I will be slowed down. Yeah, I get that. But Euclidean distance, length of the vector. So let's do this. Let's find the Euclidean distance of the arrays already in there. So this is simple adding. Have to be the same shape to be added together. Okay, look at the norm. Oh, capital letters. Okay, so mathematical length of a vector. So when we're talking about, let's pull back up. We were in this notebook yesterday. It might have been this one though. I'm spelling something wrong. No, it's not there. And maybe there is none. See if they use norm. Yeah, so when we're here and we're talking about building this robust PCA to remove the background, what we're doing here is removing the norm, not removing, but multiplying the Euclidean distance. And I'm going to 49, PCA. Let's pull it up. We're looking at this formula is, I believe, yeah, that's what we're trying to build. So when we're looking at this convex optimization, see, more theory. So when we're talking about converge, lines 4 through 5 solve this. Methods we use Facebook's fast randomized PCA, which they put in another fast randomized PCA. Results, the algorithm again, page. Okay, so this is the algorithm for this code. And if I look here, and we talk about the Euclidean norm, or sum of all squares, each element, where is that here? So I guess I don't understand why we're doing this normalization of Z. Okay. So let's see. Let's see if we can't Google this and get something fancy on someone talking about why we normalize Z, because it might mean something. I'm going to see if anything pops up. Well, read the documentation may help. Let's see. The function is able to return one of the 8 different methods with infinite. So this is order of the norm. See table under notes. So we're doing Fro. So we're getting the Frobenius norm. So what is the Frobenius norm? Wolfgang alpha. Sometimes called the Euclidean norm, a term unfortunately also used for the vector. Oh yeah, this explains so much confusion. Why can't we mathematicians come up with unique wordings? It is really frustrating me as a learner. Like, can we re-standardize some of these names? I'm just saying, shouldn't be this difficult to understand what we're talking about and when. Okay, so the Frobenius norm can also be called the vector norm. And this is what we're talking about doing. Well, this must mean something else as well, because I don't see anything like that in this formula. No sum unless x plus 1 is the summation. But this looks like ERR normally means error. And we watched this video because I got confused, but it doesn't really walk through the code. It has the assumption that you understand baseline of what they're doing, which I don't because I haven't been in college in a decade. Okay. Let's go back here. Can we find out? I don't think we can find out. Because I don't see any square roots. And I feel like if this formula is about square roots, shouldn't I see square roots here? Or when would I be taking it? So let's maybe go down to the big formula here. So there, if converged, this is an if condition based on, so this is while not converged, do this, and while. So if it converges, okay, so this is a check for the converging. Okay. Ooh. That was killing my brain. That was killing my brain. I guess I should have read more down into the code itself. Because then maybe I wouldn't have been so confused. Okay. Let's look at what's next. All right. So the next part is, this is checking for convergence. And if you don't know what checking for convergence is, it's kind of where the things meet. So check. It's better on a graph. Convergence test. We have a graph. I don't have a series to look at. It's much better on a graph. Like there's rules of convergence. I wonder if maybe I need to pull up Desmos, make my own graph. Much better on someone else's graph, I think, though. See, the thing is, there's different types of math learners. Like not everyone understands math algebraically. Some people understand math geometrically, and you can come at it in either direction. But it really is frustrating that because a lot of the more genius of our kind okay, there we go. Let's type in a formula. Can get the algebra that they don't also show it conversion in I plus equals 1. Equals 1. Okay. Let's do 2. Let's do the one down there. That'll be better. Okay, so in 2 infinity. So I'm going to leave it blank, though I'm not sure how to pull up there. There we go. To infinity and beyond. Okay, so maybe I can't put that at the top. Might not be able to do it in the software. to get a good example. Or maybe I should Google like graph of converging, and maybe that'll do it. That might help. Enter. Yeah, because it needs, but I don't have an infinity marker. A, B, C, D, E. Okay, graph of a series converging. Maybe they'll have a graph.
Thanks for clicking on this video. Today we're going to be showing how to calculate whether a series converges or diverges. Now this is going to be slightly different than the previous video we did, where I showed you how to determine if a sequence converges or diverges using Desmos. So you want to be clear about whether you want to tell if a sequence or whether if a series converges or diverges. And I'm putting a link in the upper left-hand corner for that other video where we tell how if a sequence converges or diverges. But the work is going to be kind of similar. So first thing we want to do is we want to start with n. We want to get n as a list of numbers. So 1, 2, dot, 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 100. Next thing, what we want is we want a formula for a of n. Now remember that we're talking about series, so I'm going to use a sigma notation. Now, one thing you have to do is you have to change this from n to k. Why is that? Because we're going to start at 1 and we're going to end at n. And you can't have n up here and then n down here as its own, as the same letter. Because if I did something like 1 over n squared, it won't compute correctly. Instead, what we want is we want 1 over k squared, like that. So what are we doing? Well, we're adding 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 and so on and so on and so on. And we're adding them over and over. And as we do that, we're going to plot them just like we did in the previous video. So here is our series. Now I have to adjust my x-axis just like that. So here I've got these numbers here, and it looks like it is flattening out. Now sometimes series can be a little bit difficult in determining whether or not they actually converge to something. Now the classic example of that is this. Here we have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. And this is our series. Now it doesn't look like it's flattening out. Now some people make the argument, well, you haven't put in enough points. Okay, well, let's make it 1,000 points. And if I change this number, is it flattening out? No, it's not. It's actually not flattening out at this point. So this series is not going to converge. Because by the time you reach 1,000 terms, you should be able to see a flattening out if it's going to converge at all, but it's not. So I'm going to cut this down to 100. Because depending on what device you have, 1,000 may be too much computation for your processor chip to handle. I know on my machine, it won't show 10,000, but depending on what your machine's capable of doing, it might be less than that. Let's try 1.1 to the k. Let's try this. Here we have 1.1 to the k power. So here I don't see all the points. So this is about 10, add a 0, add another 0, add another 0, add another 0. That is definitely not flattening out. In fact, it's the opposite. It's growing faster and faster and faster. Now, what if I make this negative? What is that going to do? Well, it made it a lot smaller, so I can take this number and cut it down by 0. But something else going on. It's actually down here as well. So this one is not flattening out because it's actually bouncing back and forth, positively and negatively. So this one is definitely not converging. Now, if I change this to negative 0.9, now we see that, yes, this one does indeed converge. Oops, negative 10. Yeah, let's sandwich that. Let's make it a little smaller. 1 to negative 1. Now here, it's going back and forth, kind of like a zipper. But as you go off to the right, notice what's happening. Notice that it is converging. It is getting closer and closer to a single number. It is flattening out. All right. Thanks for watching. If you like this video, hit the like button. And if you want to see more videos, click the subscribe button. To support the channel, click the links in the description below. Thanks for watching. And remember, the best way to understand something is to do it. Thanks for clicking on this video. Today we're going to be finding convergent and divergent sequences using Desmos. So when we open up Desmos, the first thing we want to do is we want to set n as a list. So I type n equals and I use square brackets. So I do 1, 2, dot, 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 100. Now you could use more for this, but I always like to use 100. Then what I'll do is I'll go over to the x-axis and I'll set the largest number for the x-axis out to 100. And so whatever number you choose for n, it has to match that because we want to see every dot. So let's take a look at something like this sequence, n squared. Now it doesn't plot anything. What we have to do is we have to plot them as points like this. Click on n. So I see 2 dots and it looks like they're going up. So if I change the y-axis number, and to make it easy, I always just go by tens. So if If it's not big enough, add another 0. It's not big enough, add another 0. It's not big enough, add another 0. There we go. And so the question is n squared convergent? Well, no. And the way you can tell from a picture is you want to look at the dots and you want to see, do the dots level out? And if they don't, well, then it's not convergent. It should be leveling off at some number. And when it doesn't, you know that it's not convergent. So let's try a different number. Let's try a different sequence. Let's try 1 over n squared. How about that? Now I see the dots way down here. So what I need to do now is I need to go back to my y-axis and start deleting zeros, because I don't need all this empty space. So I delete, 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 delete. And actually I could delete some down here, -1. So as I look, it looks like these numbers are flattening out. It looks like they're all getting closer and closer to 0. Now what if you're not sure? Well, that's easy. Go up to n and make it bigger. Put in more points. Again, just add in a 0. Now I have to go over to my x-axis and make this 1,000. But is it still flattening out? Yeah, it is. And so this is converging to 0. Now 1,000 is a bit much, so I'm going to cut it back down to 100. Now what if we're given something like this? 3n minus 1, and in the denominator, 2 minus 3n. Now I don't see anything, but it says there's a list, which means I'm looking in the wrong place, which means I need to back out. So this is about 1, so I make it 10. Back this out, -10. There it is, right there. There's my dots. And looking here, the dots are flattening out, and they all appear to be approaching -1. So this is how you can use Desmos to plot a sequence and to tell if that sequence does converge. It's going to converge if the points flatten out to a single number, and they won't converge if they don't flatten out to a single number. Thanks for watching. If you like the video, hit the like button. If you want to see more videos like this, click the subscribe button to support the channel.
Okay, so now let's go back to the notebook. Let's scroll up some and look at the optimization problem. So we're dealing with, I believe, a series. Not a series, a sequence. Oh, goodness. And they're specifically trying to do that algorithm from this paper. So combing through the resources for useful tidbits. This is the algorithm that they have. And since we're dealing with the convergence of a sequence, they're checking that it's not converged. They have to have a condition to check that it isn't convergent. Got it. So you have the shrinkage operator, which is this. And they say it operates on an augmented Lagrangian, which I don't know, Lagrangian, whatever that is. This is that. It's a multiplier algorithm. A generic Lagrange multiplier algorithm would solve PCP by, I keep making it smaller so I can see this, but I need to make this smaller so I can see that because I'm blind. We've been through this a few times. Christina is blind. I don't know why they're just browsers. That's kind of frustrating. Avoid having to solve a sequence of convex problems. Recognizing this. They keep saying it's easy to show, but I would question what you mean by easy to show. So here they take the absolute value of m and they subtract tau, and they get the NP sign. Let's pull back up the not a linear algebra function, not a math function. Maybe I should just Google. Returns the element-wise. It returns an element-wise indication of the sign of a number. This turns the sign of the number times, as long as it's on the right interval. Got it. Okay. So we're looking at this again. So if we go back to this This is where we're checking that S, you take S, is greater than 0 from 0 to S. Wait, hold on. What is the rest of the where statement for NumPy? Let me not presume because I will get it wrong. Return elements chosen from X or Y depending on the condition. So values from which to choose X, Y, and condition need to be broadcastable to some shape. Yep. So yeah. You can choose X or Y and broadcastable to the shapes. So these are the broadcastable ones, and it needs to be greater than 0. Okay. So I'm not sure what tau is yet. So we're going to go back to here. Figure out what tau is. You know what? It might be better to Google tau. See if a symbol pops up. Yes, I get that it's physics. I knew that. What is tau in math? Constant is ratio of a circle's circumference. Well, that's unfortunate because I didn't know we were dealing with circles. Orientation twist of a curve is the value of tau. So tau is a mathematical constant. It's 6.28. So did we pass 6.28 in here? Where did we use shrink at? Shrink. So we passed x2 minus L lambda mu as tau. I guess we're dividing lambda by mu to get tau. So in that case, lambda is just 1 over np squared m, and mu is this over here. A norm up. Yeah, I wish they'd walked me further through, but it's okay. We're going to figure this out. Kind of. So this is mu. I believe that's mu. This. Yeah, mu. Okay. So let's look up what we're doing with mu. So mu equals k times 1.25 over op norm. So let's see. How do we calculate mu? Sum of x over n, which is not what we did here, because we have k. Like, what is k? We just have k sitting here. Unless that's one of the things we pass in is k. No. I'm probably, okay, it's 10. I'm definitely blind and I have a headache. So k is 10. So we set k to 10 and multiply 10 times 0.25. The reason why we're setting k to 10, I guess you can change your sub. Okay, got it. So this is the k. K is 10. We can change this because it's a sub. And we're going to go k plus 1 would be like 11. So why are we multiplying 1.25 over the norm to get mu? Let's see. Actually, let me look at the formula again. So mu times 1.25. So this mu to the negative 1 might need to be what I need to be searching for first. This is mu. This is mu to the negative 1. Mu bar, I guess, is this mu to the negative 1. Rho is k times 1.5. But what is rho? Let's see. I don't see rho. If that's rho. I don't see rho in this formula, so I'm not sure why we have rho yet. That is something we'll have to figure out. And then norm of x. Okay, so this is the x. We take in the m, return underscore SVD m1. Okay, so that's what they run into the Facebook PCA to get the single vector decomposition. So I'm guessing, let's scroll up, they should have the single vector decomposition up here, or I need to get, another file hold up because okay, I'm going to pull up the previous lessons file, see if it has the formula. That needs to go over yonder. Okay, I'm going to be getting off soon. Trying to understand math with a headache is not a great idea. Okay, so they're just using built-in functions for SVD. So let's look up what I wanted to do. Not what I wanted to do. Okay. So let's look up Facebook PCA and just see what it does. Here we go. So it can do PCA, eigens, norms, moles, whatever we're talking about here. I just want the PCA. Still not to a PCA. Maximal. Oh. It said it was a page. There we go. So we need to pass it A, which is our M. That's what we're passing into the function here, or whatever our M shape is that we're setting it to. We need, their default is k equals 6. And we set instead k to the rank, which is, I have no idea, whatever the second value past SVD was. So let's go back to the measure function. Where did I see this at? Oh, I was looking. It's in the SVD function. So if I called SVD, we called it here. So they set the rank to 1. And that's it. The other given here was raw equals true. What does raw equals true do for us? Centers A. That just gives us center. Okay. Whoa, my brain. So we got through this. So we know what this is doing. They're getting the minimal rank of the minimal shape of 1. Which, now I have questions about why we're doing rank 1. So I guess that might mean to look at the equation. And I'm guessing because where are we getting the rank from? I'm guessing because it's not like going over. Well, it's a single vector decomposition, so it's 1 vector. That would make sense to me. Okay, so we'll pick it back up to figuring out why we're doing this. Because I don't know. All right. I'll see you guys tomorrow as we try to get through vector math, but I might need to, I don't know. I feel like this is the least successful week so far. Doesn't seem to be a lot of resources. I might need to order my thoughts into how to approach learning this differently and see what others might be available. I think Deep Learning AI has some as well. All right. See you guys tomorrow.